In this video, we're going to talk about logic circuits. Circuits are gates that have been combined by using the output of one gate as the input for another gate. Just like with gates, we describe the circuits by using Boolean expressions, logic diagrams, and truth tables. Here's an example. We have two AND gates. Here's an AND, here's an and we have an OR gate. Inputs A and B go into this first top AND gate. So we have A and B. This bottom AND gate has A, you see the little joining symbol here, and C. So we have A and C. The output of A and B goes into the OR. The output of A and C goes into the OR. So the final circuit result, X, is equal to A and B or A and C. As we move forward, keep in mind that Boolean values can be either 1 or 0, true or false, or on or off. There are two types of circuits, combinational and sequential. In this course, we're only going to talk about combinational circuits. The number of inputs will determine how many different combinations we can have. In the example that we have here, we've got A, B, and C. We've got 3 inputs. Now, if each input could either be a 0 or a 1, we know that we've got 2 to the 3rd possible combinations, different combinations, for a total of 8. And the way that we write our truth table is we write it in ascending binary order. If we look at each line, we see A, B, and C are all 0, which would be our binary 0. The next line, 0, 0, 1, is 1. 0, 1, 0 is 2. 0, 1, 1 is 3. 1, 0, 0 is binary 4. 1, 0, 1 is binary 5. 1, 1, 0 is binary 6. All the way to the last row is binary for 7. Now, we're going to recommend that you write and create your truth tables in ascending binary order. So basically, you've got a binary table here. What we then do is we create columns for each of our intermediate results. And in this diagram, I've labeled the intermediate results as D and E. So if we look at D and E, D is A and B. Well, and says it's only going to be true when both of the values are true. And the only time that both of the values are true are in the last 2 rows. So those are both 1s. All the other rows are 0s. We then have E, which is A and C. And the only time that we see both A and C being on is in this row and in the bottom row. So we have those both on. And OR says we're going to have be true if one or both of the inputs are on. We're going to look now here at columns D and E. So D or E. And as we look our way down, we'll see that we don't have any 1s We don't have anything on or true in any of these columns, any of these rows. But the last three, we've got a 1 here, a 1 here, and we've got 1s in both. 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. And again, this circuit can be described using the Boolean expression A and B or A and C. Taking one of these combinational circuits, we can ask the question, what is our output given a given state for A, B, and C? For example, if we look for when A is true, B is true, and C is false, what is the output? Looking down, looking for A is true, which is down here on the second half, and B is true over here, and C is false. So this row, A is true, B is true, C is false. We can just look it up, and we know our output is 1. So our output for that, X is equal to true. There's more than one way to describe a given truth table. Or putting it the other way, we can have multiple circuits and multiple Boolean expressions that produce the same truth table. And the way that will determine whether two circuits or two Boolean expressions are equivalent is if they have the same truth table. So what we'll do to prove it, if they're equivalent, we'll produce the truth table for both of the circuits. And if the output, if X column is the same in both of those truth tables, then the two circuits or the two Boolean expressions are equivalent. Now let's take a look at this Boolean expression. We've got A and B or C. So we've got B or C in parentheses, so we evaluate B or C first, and then we do an AND of the result of this. We have our Boolean table. Notice that it's in ascending binary order. We'll look at B or C and determine when will be true or false, and it will be true if either B or C are true. And lastly, our X, our output, is going to look at A against the column we just created, B or C. And that will give us our output. So this is for the expression A and B or C. Now we've already looked at this circuit. We know that this is A and B, A and B, or A and C. So if we take this truth table and compare it to this truth table, we will see that the outputs are identical. Again, having done these in ascending binary order, we know that our outputs are in the correct order to compare them one against the other. And what we'll see is we've got 5 zeros in a row, followed by 3 ones. That's what we have here. 5 zeros in a row, followed by 3 ones. So we can say that these two circuits, or these two Boolean expressions, are equivalent, since they both produce the same truth table. Let's figure out what the Boolean expression would be for this. We have an OR here. We have a NOR here. It's a NOR because it's the OR with the negation symbol. And this is going to be an AND. So top, down, left to right. So we have this gate is A and B. Excuse me, A or B. This gate is C or D, but it's negated. We're going to take the output of those two and AND them. So we have A or B as one expression, and we're going to AND it with C or D not. Or and a NOR ANDed together. Given a Boolean expression, we can plug values in and see how they evaluate. So let's assume that for this Boolean expression, we want to evaluate it when A is true, B is false, C is true, and D is false. So the first thing we're going to do is replace the A, B, C, and D's with trues and falses. So A is true, B is false, but negated, or C is true, D is false as our AND, and that's negated. So we then work inside everything. We have true and false not is true, or true and false is always going to be false, negated. True and true is true, or false not is true. A true or a true will give us a true. And that's it for logic circuits. If you have any questions, let me know.